Good afternoon to everybody, and welcome to the webinar session of today. This is going to be the first lesson about how to create a protocol with the Smart Analyzer application, starting from kinematics data that have been collected by means of the BTS Smart 3D Motion Analysis System. This is the agenda about the topics that will be discussed during this first lesson. We will cover all the required steps to create a new protocol starting from scratch, starting from the creation of the model of the markers by means of the Smart Tracker application, going through the tracking of the trial to get the 3D trajectories of the marker over the time. And then we will switch to have a look at some algorithm that can be used to process the kinematic data. In particular, we will talk about how to perform trajectory interpolation, how to create some virtual points, how to compute a 1D, one-dimensional angle, how to define some time events, how to compute local maximum and minimum over a trajectory, and how to compute the angular range of motion, for example. As an example on today, we are going to use a simplified model of the upper arm that we want to use to analyze the flexion extension movement of the elbow. We have already recorded some data where we place some markers on the subject, considering the movement that we wanted to analyze. That in this simple case was the flexion extension of the elbow. To do that, we placed 7 markers on specific body landmark. As you can see on the image, we placed 2 markers on the right and left acromion, 2 markers on the medial and the lateral epicondyles of the elbow, and 2 on the radial and ulnar styloid processes. Then on the back, we place 1 marker at C7 spine level. So basically, we are going to show an example where we used these 7 markers to measure the flexion extension movement of the elbow during a flexion extension task. So now I'm going to start with the practical session. So now you should see this Smart Tracker application, which is the application that we have to use to perform the 3D data tracking of the data that we have recorded with the smart infrared cameras. To load a trial into the application, we have to click on Open. After that, we will see a list of folders that contain all the recorded data. Otherwise, as another option, we can choose the Open file, and from there we can browse into the directory that is in your computer, which contains the desired file. I'm now going to start with the first option, so I'm going to select Open, and I'm going to select the Webinar Smart Analyzer folder that contains the data that I'm going to show you as an example. I want to start by considering the trial number 1, and you can see, as you can see, we have on the side of the name of the trial a cross icon. That is to sign out that this trial contains some raw 2D kinematic data inside. In addition of that, we can have other icons. So for example, the icon related to the EMG signals. That means that inside this file, we have also information about the electrical activity of the muscle. Or we can have, for example, the movie icon that is to sign out that we have also a video recording linked to this trial. Or we can have the icon relating to the force vector. That means that we have also kinetic data that have been recorded within this trial. And so on. We can know about every portion of data that we can find inside each trial just by looking at the related icons that are displayed close to the name of the trial. So I want to start to load the trial first. Okay, so the trial is loading, and as you can see, As soon as the trial is loaded into the application, the 3D reconstruction algorithm is applied to the 2D raw data recorded by each camera to give us the position of the marker into the virtual 3D workspace. It is possible to navigate within the volume, so you can rotate into the 3D space by moving the mouse with the left button of the mouse key pressed. If you press also the Control key on your keyboard, you can translate and move it around and move the workspace around. If you select the Shift key on the keyboard, you can zoom in to have the image closer or zoom out to have it far. So this is the one that it's shown here is the global reference system of the laboratory with the origin and the three orthogonal axes. So you can see the X, the Y, and the Z. Its position is defined during the calibration procedure. So the 3D component of each markers are defined frame by frame respect to that position. If we click on play, we have the chance to see those markers moving while the subject is performing the movement over the complete acquisition. Otherwise, if you prefer, you can also play the movement frame by frame, going forward or backward. The second required step following the 3D reconstruction is the labeling of the marker over the complete acquisition. That means that you have to assign a specific label to each marker trajectory during the entire duration of the acquisition. And this is mandatory if you need to apply a protocol to the set of the recorded markers. Imagine, for example, that you're going to use a given human body model, and to apply it to your setup marker, you have to pass to the model the information about who is the meaning of each marker, and that you have, for example, one marker on the left acromion, and that you have one marker on the right, and so on. Within the Smart Tracker application, you have the chance to associate a certain model of marker to a certain trial that you have just loaded into the application. So we can have a model of marker in order to have something to which everybody can refer to in the future. We have two options. We can click on Open Model to open an already defined model. Otherwise, we can click on New Model to start creating a new model starting from scratch. And in this case, a new window will appear from where we can start drawing our model by using the tools that are on the left of the window. So now we are going to start defining the 7 markers. So I can select the second tool in order to add new markers to the protocol. As you can see, this tool, the name of this tool is Marker Creation Tool. Then I have just to click on the black window to draw the markers. So I'm now going to draw 7 markers for the 5th and the 6th. Remember that, in general, it's not important the position of the marker over here, because this is just a draw. But it is important to position them in order to remind us in the future which are the bony landmark point that we have used. Okay, so if you want, if you prefer, you can also select this tool, and you can move the position of the marker if you prefer. Okay. Then we can use the third tool that is on the toolbar, that is for creating a link between two markers. As you can see, if I select this tool, its name is Link Creation Tool. So I can select it, and as you can see, once I click on a marker, it becomes yellow, and after that you have to select the marker you want it to be connected with. So marker 1, for example, then I want to link marker 1 with 2, the 2 with 0, okay, and then the first with the third, the first with the fourth, and the fourth with the third, and so on. This with this, this with this with this. Okay, so okay, the next thing that I want to show you is that for any reason you perform any mistake, so for example you connect this marker with this marker, if you did any mistake, you can use the erase button to erase the undesired link. Okay, so this is our setup of marker, but in general calling them marker 0, marker 1, marker 2 and so on cannot be helpful for practical usage in the future to help us to remind which markers are they. So now I'm going to change the label of each marker. To do that, I select the tool with the A icon here, that is the labeling tool, and when you select it, another window will open, from where you can start editing the label of each marker. Okay, so now I'm going to rename each marker. So the first will be C7, the second will be the right acromion, the third the left, the fourth is going to be the lateral elbow, this is the medial elbow, this is the lateral wrist, and this is the medial wrist. Okay, after that, if you want, you can also move the position of each marker within the list by using this arrow. Okay, so I click on OK. After that, after you finish creating your model, you can save it. To do that, we can click on Save Model, and in this way we will have our model available into our database, and so that we can reuse it again in the future. So I'm going to save the model. You have to type the desired name, so sample model. Okay, and I want to sign out which is the extension of the file we are going to save. So the extension for model file is XMF. Okay, so I'm going to save it. Now that I have defined the model, I can start by associating the model to the collected data. So in order, if you want to label each marker, you have just to click on it, and the list of all the available markers will appear. So this is going to be the C7, this is the right acromion, this is the left, this is the lateral elbow, the medial elbow, the lateral wrist, and the medial wrist. As you can see, also the links belonging to the marker are automatically applied to the marker set. And now we can move our 3D, or we can click on play just to check that the trajectory assignment is complete over the entire duration of the acquisition. So now I have voluntarily created some gap into the trajectory, because after that I want to show how you can perform any interpolation within the trajectory. So after that you have label, you give a label to each marker, you can save the file. When you click on Save, a window with a list of all the available markers will appear. From here, you can choose which marker trajectory you are going to save. For example, you can exclude some of them if you want, or you can, normally, you have to select all of them. And then you can click on OK to save it. OK, so now we can close. So the next step is to switch over the Smart Analyzer application to start by processing the data that comes from the acquisition. Now you should see the Smart Analyzer application. As you can see from here, you can see that basically the software has a similar layout. We have here the chance to open a file, to creating a new protocol starting from scratch, to open a protocol that already exists, to change some settings of the application. For example, if you click on setting, we can change some parameter of the operator, we can change the setting of the printer, and so on. If, for example, we click on measure unit, you can see that from here we can change the measure unit for each kind of variable used by the application. So, for example, we can choose if we want the 3D points in meter or respect to millimeter, for example. Or we can also define which is the number of the decimals number that I want to have displayed, or how many standard deviation values I want to consider as a confidence range. Okay, within the Open menu, you have the chance to open a data file directly from the database as we did before. Otherwise, you can choose for Open File, and now you have to browse into the directory in your computer. Another option can be to open an archive file that is a file with an extension of MDX, and which is usually used to store all the data contained in an acquisition coming from both the original file and also the data coming from the protocol operation. So normally an archive contains the results coming from a protocol. Otherwise, you can import a file containing a normative band, which has an extension of AENB, which contains information about the normal range of data. Otherwise, you can import a TXT file or other kind of file format that can be loaded into the software. One example is the C3D file. So in this case, I'm going to click on Open. After that, a window will appear containing, again, the folder that contains my data. So I'm inside the Webinar Smart Analyzer folder. And as you can see from here, now we can see that also another icon is on the side of the name of the trial. Before we have just the cross icon. Now we have also the icon related to the 3D markers. That means that the trial has been already tracked. Remember that you can load into the Smart Analyzer application just tracked file. So file that contains information about 3D trajectories. Okay, so as you can see, as soon as you load the trial into the application, the same 3D workspace window appear, within which we can again rotate and move as we did before. So on the left side of the screen of the menu, you have the data panel, which contains all the trials that have been loaded into the application. So basically, in this case, you have the TDF file that we have just tracked, and that contains information about all the tracks related to the 3D point that we have placed on our subject. These trajectories are given respect to the global reference system, that is the one that is shown here. That is the reference system that is defined during, again, the calibration procedure. For each point can be visualized or into the 3D workspace, or you can choose to visualize the 3 different components of the trajectory into a graph. So in this case, we have visualized the 3 components for the C7 marker, and we can see the X and the Y and the Z component. Okay. So in every TDF, you will find all the data that you acquire. So in this case, all the 3D point tracks, and also the global reference system. So inside the reference, we have the information about the position of the global reference system. So about the origin and X, Y, and Z axis. But if you load a trial which contains also EMG data, force platform data, and so on, in that case, you will have into the TDF file also additional folders that will contain also this type of data. Now we are going to close the 3D, and if you want to open it again, you have just to drag and drop it, and you will have again open. Okay. From the menu toolbar, you have the chance or to open a protocol that already exists, or to create a completely new one. To start from scratch, we are now going to click on a new protocol, and as you can see, we will have this white and empty page in which we can start to add all the desired tools useful to get the results of our analysis. First of all, it is important to understand how the tools are organized. On the first column, you have all what is related to 3D variables, basically everything that has 3 dimensions. So, for example, a 3D vector, a 3D reference system, a 3D point, a 3D velocity, acceleration, and so on. If you switch on the right side, you have similar tools, but for 1 dimension variable. So, for example, you have a scalar, a 1D point, and so on. So, in order to understand which blocks of operation I have to consider, I need to know the dimension of the variable I'm going to compute. So first of all, I need to know if it is a 3D or 1D variable, and which will be its physical meaning or its measure unit. So for example, I need to know if it is a scalar, if it will be an angle, a velocity, or an acceleration, and so on. So for example, if I'm going to compute an acceleration, I have to look inside the acceleration blocks. Okay, because at the end of the operation, the output I'm going to have will be an acceleration. For example, if I want to compute the temporal mean of a 3D track, as the output will be again a 3D variable, I have to click on 3D markers, and the required operator will be within the list that is inside. So for example, I can choose the mean operator, and I can click on temporal mean. As you can see from here, each operator has 1 or more than 1 inputs and has just 1 output. To get an output, you have just to drag and drop the required input into the operator. And as you can see, if the related dot becomes red, as it is in this case, that means that the chosen variable can be used as an input for the operator. And so you can see the output. Otherwise, if you drag and drop an input that is not correct, so for example, as you can see in this case, In this case, you can see that the dot will become gray. And so that means that the input that you are going to use is not a correct input for that operator. Okay. And at the end, if you try to drop it, you will have this error message that reminds you that it is an invalid input data. Okay, so if you move the mouse close to the block, to the operator, you can also visualize the meaning of the operator. So, for example, in this case, we have temporal mean of an object track. Okay, if you select the operator and if you select the right menu you can get from the mouse, you can choose between copy or remove the operator. So now I'm going to remove. So this was just an example about the layout of the Smart Analyzer application. Now we can start using some operator to perform our analysis. First of all, we can start by performing an interpolation over the 3D points. That is a useful operation when you have some gaps into the trajectory, due to the fact that in some frame the markers cannot be visible from some camera. And so the position of the marker cannot be reconstructed. So let me show you an example. As you should remember, I've told you that I have voluntarily created some gaps into the collected data. So, for example, in this case, you can see that we have some gaps into this trajectory. So, if I want to fill these gaps, I can choose to perform an interpolation within the trajectory. To do that, I can select the 3D point operator, and then I can select the interpolate track option. Okay, so now I have just to type the name of the output. So I'm going to use C7E, where I stands for interpolated. So in order to get the results, I have just to drag and drop in the input. I can start by copying the same operation because I have to do the same for all the marker. So I have to type the name of the output, T acronym. Okay. This is for the left acronym. I can say the same for the for the lateral elbow. And the same for the medial. So as you can see, you can just copy one operator and paste it. And what you have to do after that is to rename the name of the output. I'm going to do the same also for the lateral wrist and for the medial. Okay, so for the first, the lateral wrist is the input, and for the last one, the medial wrist is the input. So now I want to show you the results. Before, as I have already shown you, we had a gap within this trajectory, and after that you perform the interpolation, you can see that now you have a complete trajectory over the complete acquisition. Okay, so after that you have performed this operation, we can start by computing our 1D angle to perform the analysis that we want to perform, that in this case is about the computation of the flexion extension angle at the elbow level. But before starting to do that, we need to define some virtual point, because in order to compute this angle, I want to use the right acromion, and then I'm going to use the medial point between the two markers that we have at the elbow level, and I'm going also to compute the middle point between the marker that are placed on the wrist. In order to compute these two virtual points, as the output in this case is going to be again a 3D point, we can select the 3D point operator, and within the available list we can choose this option, that is the 2 points and scalar. As you can see, this operator requires 3 inputs. The first two will be the two markers, in this case the lateral elbow and the medial elbow. And the third point is going to be the scalar. So in this case, as we are going to compute the middle point between the two markers, we have to define a scalar which value can be set as half, so 0.5. So half, and the value is 0.5. Okay, and the name of the output in this case, this is the medial the middle elbow point. As you can see, we can also drag and drop the results into the 3D workspace. So this is the virtual point that we have just created, and as you can see from here, we have in this way created a marker that belongs to the same line between the two markers, between the lateral and the medial marker, and that is placed exactly in the middle between the two. So now we can do the same also for the to compute the midpoint at the wrist. Okay, and also in this case I need to use the lateral wrist is the first input and the medial wrist is the second, and I can use the same half scalar value to compute the point that is in the middle of the two. And this is the results. So now I can start computing the angle. In this lesson we will just talk about 1D kinematics. So I can click on 1D angle operator, and within the list you can choose between two options. The first is for computing an angle between 3 points, and the second is to compute an angle between two unit vectors, so two vectors. And the results will be the same, but I'm going to use the first. So I want to compute the angle between 3 points. In this case, you can see that this operator requires 3 inputs, and they will be the 3 points. So in this case, they will be the right acromion, the middle point between the lateral and the medial epicondyle of the elbow, and the mid wrist point. Okay. Remember that you have to use as the second operator the marker that is at the vertex of the angle that you want to compute. So in this case, the second operator has to be the medial, the medial elbow marker. The first can be the right acromion, and the third, the middle wrist. I have just now to rename the output, so it's 1D flex x elbow angle. Okay, and now I can show you the results. So as you can see, we get an angle which has a value that is around 170 when the elbows is in fully extension, and that decrease its value during the flexion. If you want, you can also play the 3D, and you can see while the graph's moving during the execution of the movement by the subject. Okay, so now we can, for example, continue by computing the range of motion of the angle. That can be considered as the difference between the maximum and the minimum value we have. So this can give us an idea about which is the maximum movement that this angle can cover. So we can start to compute the maximum over the track of the angle. To do that, we can select on event operator, and then we can choose the option event sequence on one object. So the name of the output will be peaks time, and the input is the 1D angle. I can now ask to the application to compute the time where we have maximum automatically. So I can, as you can see now, we have some vertical lines which define the position of the maximum. If you want, you can also select other events manually. I can do the same for the minimum value. Mean. And again, the input is the 1D angle. So now I'm going to look at the local minimum over the trajectory, and as you can see here, the algorithm is able to do that automatically. Okay. After that, I have to, let me just show you the results. So the peaks time is the time sequence of events where we have the maximum value of the angle, while the second sequence is the sequence of time in which we have the minimum value of the angle. So now, if we want to compute the range of motion of the angle, we need to know which is the value of the angle in correspondence of each event. So in order to do that, we can click on 1D angle and look at within event operator and select event defined value. Okay, so peaks is going to be the name of the output. In this case, the first input has to be the angle in time, and the second input has to be the event sequence. So in this case, I can have as results the sequence of the maximum value of the angles. As you can see, now I have an angle. I can do the same for the minimum. So the first input can be the angle again, and the second input, the sequence of the minimum. And this is the results. So now I can compute the average between all these values. To do that, I can click on here, and I can select the option max mean mean operator and select the sequence mean operator. So the first output will be the mean max angle value, and the input is the peaks, and this is the results. Okay, and I can do the same for the minimum. Okay, for the minimum, mean angle value, and in this case the input has to be the sequence of the minimum value of the angle. And so, as you can see here, this is the result. So now we can finish by computing the difference between the two values that give us an idea about which is the range of motion of the angle. To do that, I can click on 1D angle and choose for map operator and select the difference between the two objects. From angle, and the first input will be the max, and the second is the minimum. So this is the difference between the two that give us an idea about which is the range of motion. Okay, so when you finish by creating a protocol, you can save it. Okay, so in order to save it, we can click on Save Protocol. And in this case, you will create a file with an extension of EPX. So you can type the name of the protocol, sample protocol. Okay, and after that you click on Save. Okay, this window will open from where you can type a protocol description, sample upper limb protocol. Okay, and after that you have to at this point there is the point in which you have to pay attention to, because on the right you have the list of the files that are being used to create the protocol. In this case, we have just one file. At this point, the software is asking us about the sequence, which is the sequence of the trial that we have used to create the protocol. Now we have just one file, but imagine the case that you have created a protocol which analyzes, for example, some variables from a trial that can be, for example, the standing trial, and which perform other analysis starting from another trial that can be, for example, the walking trial. So in this case, you have to tell to the software which is the correspondence between the trial loaded into the protocol and the files that will be used to compute the requested protocol results. So in this case, as I have just one trial, I can just use this. And if you select the multiple option, that means that everything that I have created into the protocol, so all this computation that I have performed for the single trial, first trial, trial 01, will be applied automatically once you will load more than one trial into the protocol. So if I click on that, if I click on OK, I have now saved a protocol that can be reused in the future, and if we will load more than one trial into the protocol, all this computation that we have performed on the trial number 1 will be applied to all the trial that we will load. But we will show you about how to do that during the next lesson. So I would like to thank you everybody for your attention, and see you on the next webinar. Okay, bye bye. Ciao.